We are live now.
Okay, great. Good evening, everyone. Welcoming you all to the 29th session of the Vertical 3. As you all know, we concentrate on open and proprietary software practical sessions every evening. So today we have two sessions from Schrodinger from 6 p.m. till 8 p.m. Myself, Giri, one of the coordinator for Drug Discovery Hackathon. And as usual disclaimer, please do not share any personal details during this online meeting. And Drug Discovery official hackathon registrations have been started. Please log in with your MyGov account to register. And today we had already spoke about Drug Discovery virtual tool room. So the registrations will be active very soon, early next week. And also, all of you kindly type your questions in the live chat during the question and answer sessions. We will try to answer those questions. And today we have two sessions. One is on molecular dynamics simulations and trajectory analysis by Prajwal, and de novo molecular design by Pritesh. So over to you, Prajwal. Thank you.
Yeah, thanks, Giri. So I hope I'm audible.
Yes, you are.
Okay. Just a minute. I need to keep my presentation up.
Sure.
So what about presentation? Is it visible?
It's coming up. Yeah, yes.
Okay. Now, so seems okay?
Yes, please go ahead.
Yes. Just a minute. So yeah, Giri, what about now? Is it fine? Visible? Audible?
Yes, Prajwal. Everything is good.
Okay, great. So thanks again, Giri, for the opportunity, and thanks to Drug Discovery Hackathon team for giving us an opportunity to present on the topic. So without wasting time, I just start my presentation. So let's see, today I'm specifically going to focus on Desmond, which is a tool from Schrodinger. So the thing is, with Desmond, like it is very much easy to perform MD simulations and to perform analysis. So my complete focus will be on specifically focusing on how easy it is to perform MD simulations using Schrodinger Desmond. And not only performing MD simulation, but how easy it is to perform analysis, MD simulation analysis using Desmond tool. So that will be my primary focus. Along with that, I'll be also covering some of the basics of MD simulations in very easier manner, which I feel. So other than that, there are plenty of literatures available on basics of MD simulation. One can please go through all that literature, but I feel to discuss all things in not in much detail, but at very basics level and in very easier way. So this is what my primary focus will be on. So let's start the presentation. So before starting presentation, you can see I'm working with Schrodinger as a senior scientist, and this is my email ID, which is prajwal@schrodinger.com. And if you are interested, you can note it down, ID as well as phone number for further communication. So in case there are questions which are unanswered in this session, maybe because of time limit, we can always discuss it further on email. So please feel free to write me an email with your queries related to Desmond and MD simulations. So I mean, before going into MD simulations, first thing we need to understand, and probably everybody of you know about it, like what is the basics of drug designing, or how do drug binds to the enzyme. So as you know, it all resembles to the lock and key model. So enzyme substrate complex is same as that of lock and key model, and the whole idea of doing drug designing or drug discovery is to find out the best key amongst all available keys, or it is to not only to find out best key, but to design a new key for your particular lock. And here our lock is a enzyme, or receptor or any biomolecule. You can see like proteins, DNAs, RNAs, antibodies, antigens, or any other biological macromolecules. So that can act as a receptor and it resembles to the lock. So basically the thing is by using molecular microscope, means molecular microscope is nothing but our software, molecular modeling software. So by using molecular modeling software, we can see basically everything in a 3D view, and in 3D view you can see what is present inside your lock, and not only lock but what is present inside your receptor. And if you come to know about what is the shape of receptor, how it looks like, you can better design a key or a substrate or inhibitor molecule against that key. So basically receptor, I mean, it's not only the shape, but there are various properties which are present in the receptor, and we try to see what are those properties, like for example hydrogen bond acceptor, hydrogen bond donor, hydrophobic, hydrophilic, whether there are charged residues. So all those things we see using molecular microscope and a software, basically molecular modeling software. And accordingly we try to use all those complementary features in our molecule so that we can design a better molecule. But very important question comes here while designing a molecule is, though it resembles to the lock and key model, but whether your lock is really static in nature. So in your biological system, the enzyme or a receptor is not at all static. Though lock looks like static, but enzyme is not at all static. So the thing is, whatever we perform using molecular docking exercise, that is considered as a high throughput virtual screening method, in which we consider receptor or lock as a static, but as such in biological environment it is not at all static. So somehow we need to consider the flexibility of this receptor in in our software, and we need to treat it as a flexible. That will be the best possible way to treat it. So as you know, all of you from past few sessions, we have seen how we can perform molecular docking exercise using Glide, which is included in Schrodinger suite, and how easy it is, how fast it is. But with molecular docking exercise, as I already said, it is a high throughput virtual screening method in which we normally consider protein as a rigid. So there are no conformational changes happening in a receptor while doing molecular docking. But for ligand, is for key, there are various type of conformational which are possible, and we try to explore all those conformation in the molecular docking program. So that is why in traditionally molecular docking program or method is called as rigid receptor docking. The ligand is flexible, but receptor is rigid. So in this way, you can screen millions of compound in high throughput way, but still the reliability is less in such cases. It is always suggested to go for higher level of molecular modeling studies if it is possible for you, and those are, for example, molecular dynamic simulation studies. So as you see here, the crystal structure, basically crystal structure, whatever is available in protein.data bank or other databases are a single frame of a complete ensemble of your flexible protein, which is crystallized by a crystallographer. So it can give you an initial idea about how protein structure looks like, what are the conformations of amino acid residue, but still there are a lot of information which is missing, and that information is the flexibility. So on left hand side you can see this is the image of static crystal structure, which looks very pretty well in ribbons view as well as in surface view, and ligand is perfectly fitted inside it. But again, this is the static structure, but in biological environment or inside your body, everything is flexible. So you can see in right hand side image, it's a protein which is very flexible in nature. This is what it mimics biological environment, and you can see the ligand, which is self-exploring the various pockets which are possible for ligand to fit in. And so basically by using MD simulation methodology, we can mimic that biological environment and flexibility of protein, and we can allow ligand to fit by its own. So that needs really longer MD simulation, and studies published in JAX in 2011 by D.E. Shaw group, and it's really an interesting paper to see. So this is what is the power of MD simulation. So if you try to relate it with our day-to-day life, so here you can see a representation of human. So whatever structure we get from protein data bank or crystallography is a static structure. See, if human is static, means in a way it's dead. But that's not the case for live human. Means it can have various levels of flexibility, like he can, its legs, its limbs are flexible, and everything is flexible. If everything is moving and flexible, it means human is live. So the same thing is applied for protein also, or receptor also. It can have various levels of flexibility. So because of that flexibility only, everything is live. But if it gets static, it means everything got frozen and it will end up into dead protein. So that's the reason why while doing drug discovery, we need to consider the flexibility of your receptor. So how to consider it? So there are various methods to consider it. Out of one is molecular dynamic simulation. So far, there are three methods which are established in virtual screening protocol, in silico virtual screening protocol, in which first method is rigid receptor molecular docking. On left hand side, you can see. So basically, this method is in which our receptor is considered as a rigid and ligand is considered as a flexible. So that's the thing. But in another method, which is called as induced fit docking, we can consider binding pocket of protein as a flexible and rest of the protein is still rigid. So that's the another level of flexibility which we induce in the software. And third level is molecular dynamic simulation, in which basically we consider everything. Everything means protein, ligand, water, ions, and whatever is present in biological system is as a flexible. And that's the higher level of molecular modeling studies, which is necessary to perform for getting your precise results or reliable results. And after doing MD simulation, you can get your research published in a good journal. So that's also one of the important aspects of doing MD simulation. So here I would like to show what is the power of MD simulation. So as you can see here, there are two images which I'm basically showing. So on left hand side, it's basically this is the MD simulation of water in liquid phase. So whenever water is present in liquid phase, so this central molecule is a single water molecule surrounded by many other water molecules. So whenever at a room temperature, 298 Kelvin, so basically it is in liquid form. And why water is in liquid form is because of hydrogen bonding interactions with the surrounding water molecules. So you can see here at the same time, there are 4 hydrogen bonds which are forming by this water molecule with surrounding water molecules. You can see these dotted yellow lines are representation of hydrogen bonding interactions, and there are 4 at most. So the thing is, at room temperature, it exists in liquid because of hydrogen bonding interaction. And this is the MD simulation trajectory of water at room temperature. But on right hand side image, we increase the temperature to 368 Kelvin, which is almost the boiling point of water. And while water boils, it reduces the hydrogen bonding interaction with surrounding. And now you can see this water molecule is not at all making 4 hydrogen bonding interaction. It's merely 2 or 3. So that's the reason why water boils. And this is what the physiological phenomena which happens while boiling the water, and we can capture the exact phenomena using molecular dynamic simulation methodology. So this is what I would like to focus on, the power of molecular dynamic simulations, that it can basically give you the pictorial view of what exactly happens inside the biological system. So this is one of the successful example of MD simulations to mimic biological or physiological processes. So in the brief history from where all those these things are started is here it is very much depicted in a very nice way. Like on the timeline, you can see in late 50s by Alder and Wainwright, they introduced the phenomena of molecular mechanics. to study the interaction between atoms. And so in after late 50s, like it took around 10 years to get this theory established and to actually implement it in a biological system. So in mid 60s, there was a professor called Anisur Rahman. So basically he was a very good scientist from Hyderabad, India. Then he moved to USA for carrying out his own research. So he carried out the first molecular dynamic simulations on liquid argon to study their properties. So this was the pioneering study in the field of molecular dynamic simulation. And then in the late 70s, there is another scientist called Andrew McCammon. So he did first protein simulation, means he applied this MD simulation theory on the biological molecules, for example, protein. So he did first MD simulations on it, and it was for just few picoseconds. And afterwards, like history continues. So you know like what is the current status of MD simulations. Now people have high performance computing systems as well as GPU cards, so they can perform microsecond or millisecond level of MD simulation in just one go. So rest is a history. So we just need to know like how it is started, when it is started, and how far we came. So now we have all power to perform seconds of MD simulation. So that's the thing. So in the research point of view, there are few things which you always need to consider about the MD simulation. Like what are the things which, how long I should go for MD simulation to address my problem. So you can see here there is a time scale of the MD simulation which you can perform. So it starts from, let's say, femtosecond, which is 10 to the power minus 15, then picosecond, nanosecond. So most of the time, wherever if you read the paper, you will find out that somebody has performed few nanoseconds of MD simulation or few hundred nanoseconds of MD simulation. So why do they perform few hundred nanoseconds of MD simulation? So the answer lies here, because whoever want to study the loop motion or protein motions, that can be basically studied at nanosecond level. Or if you want to study drug protein interaction, that also can be studied at nanosecond level. But let's say if you want to study some domain motions, means whether protein has various conformational state, like for example, in kinase, there are motions like loop in, loop out motion, or there are open form of protein, closed form of protein. Such motion, such studies need motion of large domain inside the protein structure, and that needs to be analyzed at microsecond or millisecond level. So it all depends on what you want to study. Like if you want to study just protein ligand interactions and want to calculate binding free energy of it, then nanosecond level of study is fine. If you want to study domain motion, then you need to go for microseconds. If you want to study large domain motions, you need to go for millisecond level of MD simulation and go on. But let's say if you just want to see some bond vibrations or methyl rotation, that can be studied at picosecond level also. So this is all you need to think of if you are working on, let's say, membranes and any molecule diffusing through membrane or protein binding to membrane. That also needs microsecond to millisecond level of nanoseconds of time period. So this is what we need to think of while performing MD simulations in your project, that which is the phenomena which I want to address. Based on that, you need to decide how long I should go for MD simulations. So in the very basics of MD simulation, like for example, it is, we all know probably that it all depends on the MD simulation is basically governed by the Newton's second law, which says like force is equal to mass into acceleration. So we can rearrange the equation into acceleration is equal to force acting on the atom divided by the mass of atom. So here you can see like from where force come into picture. So force come into picture because of intermolecular interactions, and there are ways to calculate those intermolecular interactions on each atom. So if you can see here, there are the parameter which is mass of an atom is basically a scalar quantity and it is constant for an atom. But if you see the force, so the force on the atom, we can calculate it from the acceleration. And so acceleration, like to calculate your acceleration, you must know the velocity of that particular atom at the particular time. To know the velocity of that atom, you should know what is the initial position and what is the final position of that atom. So once you know these things, the overall idea is, once you know initial position, you know force acting on it, you know what is the time, you know what is the mass. Then final thing is, you need to calculate basically the next position. So for example, here you can see it starts from this black sphere, and it ends up into the next position, which is represented in gray sphere. So you can see, like, depending on the force, depending on the mass of atom, we can calculate what is the next position with respect to initial position. And so once you calculate the next position, you just need to repeat this same equation for 1,000 number of atoms and for 1,000 number of positions. Means a lot of atoms, lot of positions. So it's all about solving this Newton's second law equation, but it's not that much easy. I just made it easy to make you understand like how it works. But there are many environmental factors which come into picture, and for example, solvent is solvation effect and any other things. Those we need to consider while calculating this next position. Means it is all affecting on the force which is going to act on this particular atom. But in the basic, the crux is it all depends on Newton's second law of motion. So we always need to solve that equation to predict the next position of atom. So means in the force field, so force field is the one which governs all that motions of atoms, because it defines the force acting on your particular molecule. So there are various parameters which are defined in the force field. For example, when two atoms are connected through a bond, like covalent bond, so though that bond is considered as a harmonic bond, means it can move around. If three atoms are connected to each other, so there is an angle which is harmonic angle, and that moves around. So because of that motion, it applies the various force on the atom. If there are three atoms which are connected together, so in which basically there is a change in dihedral angle, and that we need to calculate to calculate the force. So not only the bonded atom, but even something is non-bonded. For example, two atoms are far from each other, but within van der Waal interaction distance. So that also affect on each other for their force as well as motions. So van der Waals or electrostatic in type of interactions between atoms. So these are various n number of things which we need to consider while defining the force on the atom. So if you can compute all those things, you can calculate the force acting on the atom. So, but you basically don't need to calculate it, because it was already calculated by a scientist and it was already implemented in the force field. So this is what is the basics of force field, which we use in the molecular modeling studies, or specifically MD simulation studies. So overall, that was the basics of MD simulation. And now we will see what are the steps involved in doing MD simulation of any protein or protein ligand complex. So in very simplistic way, like you can get a protein structure from protein data bank or any other protein database. So let's see, we are dealing with the protein or DNA or RNA, so whatever. So you can get the initial structure of your protein, let's say, from protein data bank. So as we have shown in our first day presentation by Dr. Pritesh, that whenever you come across protein, you always need to prepare that protein through protein preparation wizard. And once you prepare your protein, you can use that protein for further molecular dynamic simulation studies, or you can dock the ligand of your interest inside that protein, and then you can use this particular complex further for the molecular dynamic simulations. So before proceeding molecular dynamic simulation, once you have a structure of your protein or protein ligand complex, we need to prepare our system. Prepare our system means solvate your system or put it in the membrane or whatever you want to simulate to address your physiological phenomena, that you need to build your system basically. So to build your system, we have a system builder module which can build your system in just one go, means one click. But this is the very critical step which would require a lot of time for other software, I would say. But with Desmond, it is pretty easy. We will see it in actual demo how easy it is. So once you have system builded with you, means solvated system of your protein, as well as if you are interested in studying membrane, you can put it in membrane, solvate it, put ions, adjust the pH condition, adjust the temperature and everything. And then we need to perform MD simulations based on the force fields which you are going to use. So in Schrodinger, we are using OPLS 3E force field. So once you perform MD simulation for, let's say, nanosecond range, you need to analyze that MD simulation data, and to analyze MD simulation data, there are various parameters which you need to analyze. For example, RMSD of the protein, RMSF of the protein or ligand. Then there are many other interaction parameters and polar surface area and everything. So there are many such parameters which you need to analyze. This is the traditional steps which are involved in MD simulation. But the question comes, which software to use, and whether it is easy to use, or do you need to, how much time do you need to spend on doing all those things. So with the Desmond, like, it is pretty easy, and you will see how easy it is. So but you all need to follow those 5 steps while doing MD simulation. That is what is necessary. So in next step, we will see how easy it is. So as I said, or probably in the first day of lecture, you have seen like protein preparation wizard. Basically, this protein preparation wizard is a single panel, consists of 3 sub panels like import and process, review and modify, and refine. So there are basically 3 clicks, and in just 3 clicks, you will get your protein prepared, just like explained by Dr. Pritesh on the first day. And once you have your prepared structure in just 3 clicks, you are ready for the system builder. So this is the panel which is for system builder, which is present in the Schrodinger. So this is also a single panel, and everything by default works very fine. You just need to load your protein and load your protein on the Maestro, and you can see here it automatically shows you the box around it. And just by using 2 clicks, you can get your system prepared, and within a minute. So it doesn't require a lot of basic knowledge of how to prepare it. You don't need to run commands, and everything whatever is needed to consider, everything is getting considered in system builder. Also, you can add ion, and that is also by default considered in it. You need to neutralize the system, and that is also by default considered. So basically, you just need to click, you need to 2 times click on the panel, and that's it. It will prepare your system nicely, and you can see here after your system preparation, it looks like this. The box of water and ions present in it, and your protein is basically protein or protein ligand complex is present inside the box and perfectly centered in the box. So this is what your input system, which is ready after doing system builder exercise in just 2 clicks. And once you have system ready, you are ready for the running of MD simulation. So even running MD simulation is also a one click panel, load your system and click on run. So you can also specify other parameters, like all other parameters which are necessary to perform MD simulations are considered there by default. But if you want to change it, you can change it. For example, how much nanosecond you want to run MD simulation. Here it is example of 10 nanosecond MD simulation. How many frames you want to write. So basically by default, these parameters are being calculated by software, but you can also change it. Then which ensemble you want to run it on, for example, NPT or NPET, or if there is another ensemble, constant pressure, constant temperature, as well as constant area. There are many such ensembles are there, and by default it gives you those options, but you can always change it. So there is a temperature option, there is a pressure option. So everything is present there. It also has the own relaxation protocol, like you don't need to worry about protein minimization, system equilibration. Everything is being considered inside it by default. But if you want to change it, these are the advanced options, you can change it. But even if you don't change it, it doesn't matter much because everything is very well calibrated and optimized protocol. So you can rely on it. You can specify the number of nanosecond and click on run. So it will run the MD simulation. The only condition is you need to have Linux operating system and GPU card with your computer. Then only MD simulation is possible to run. So once you run your MD simulation, you can see the MD simulation trajectory in Maestro visualizer. So here you can see the box of water and in which protein and ligand is present inside it. And you can see the all type of flexibility of your protein ligand complex water is being considered in the MD simulation. And so there are various parameters like you want to analyze various interactions. For example, hydrogen bonding interaction between protein and ligand. So those are denoted by yellow dotted lines, and there are many other type of interactions or water mediated interactions, and everything is being you can see it in just one click. In the Maestro visualizer, it is that much user friendly, and here you can see basically throughout the MD simulation how interactions are being changed, and you can analyze all those things visually. So you can see here how ligand is also moving because of this flexibility and change in interaction. So the thing is, at the end, we need to calculate all those parameters like how many hydrogen bonding interactions, which residue it is involved in. So you probably need to write hundreds of script in case of other software to analyze all those data in textual format. But with Maestro or with Schrodinger, it comes in just one click away for you. So in just one click, it will analyze all the parameters which are there and how to calculate analysis using simulation interaction diagram. So that is called as SID. So that panel is also with you. You just need to open your panel. It automatically detects protein. It automatically detects ligand, and you just need to click on run. And just in single click, it will analyze all type of possible data with that MD simulation, and images and data associated with it in proper format, so you can directly go for publication of those images. So it is just a one click away for you need to always focus on that how easy it is to perform MD simulation as well as to perform the analysis. And we will see little in detail which are the various analysis present with us from the simulation interaction diagram deviation of the protein of the ligand in various formats. So you can see here the graph along on x-axis you can see the time in nanosecond, which is 5 nanosecond, and on y-axis you will have protein RMSD and ligand RMSD. So you can see here in cyan color it shows RMSD of protein, and RMSD fluctuates between 0 to 3.2 angstrom, and I would say it is pretty stable. So you will have some fluctuations, but that these fluctuations are always in stable range. So in a way, like whenever you have fluctuations within 0 to 4 angstrom, that for your protein structure, it is considered as stable fluctuations, and you can rely on the MD simulation that everything is fine with you with your MD simulation. The same thing is applied for a ligand, but for ligand only fine. You should not have bigger fluctuations during your RMSD value. So this is one of the analysis of from simulation interaction diagram. And next analysis is your secondary structure element predictions throughout the MD simulation. Here also on x-axis you can see the timeline, and y-axis the residues, and various color bands like orange and cyan color bands are there for the secondary structures. For example, beta strand is mentioned in cyan color, and this orange color is for helix. to white, it means white is for loop, means your helix is being converted into loop, and that could induce the instability in your protein structure. So these are the things which you need to analyze from this secondary structure element analysis. Then there is another analysis called RMSF, which is root mean square fluctuation. So basically it says how much your amino acid residue is fluctuating during MD simulation. So on x-axis you can see the residue numbers of your complete protein structure, and on y-axis there is a RMSF value. So it should be as minimum as possible, and spikes means these residues are fluctuating a lot in your MD simulation. So it basically this plot is all interactive in nature, means if you just move your mouse over this plot, it will say highlight the same amino acid residue on the visualizer also, which we will see. You can also see the various bands like this faint orange color or faint cyan color band. So those belongs to the secondary structure. And one of the critical observation here you can make is the region which is present in helix region, means this faint red color bond, orange color band. So you can see RMSF value is very much low. And same thing is also applied for the region which is present in the cyan color band. But whatever is present in white color means loop region. So in loop region, because of there is a lot of flexibility in the loop, so you will always have a spike in RMSF value. Means the amino acid residues which are present there are fluctuating a lot. As well as here you can see this some green color lines are basically representing the ligand residues, amino acid residues which are making contact with ligand. So the thing is, whenever your amino acid residues are making some contact with your ligand, means some hydrogen bonding interaction or other type of interactions, means those residues are not fluctuating much. So these are the various things which you can conclude from the RMSF graph. And same thing is also applicable for the RMSF of ligand molecule. So here you can see the atoms of ligand molecule, and so how the fluctuation happens in the various atoms of your ligand. So for example, here I have put the cursor. So it is for atom 14, and same thing is being highlighted on the 2D structure of ligand, and you can see where the ligand 14 is. So in this way, if you see the atom 20, so basically 20 has much fluctuation during the MD simulation. And why it is so? So if you see the structure of ligand, 20 is the terminal atom which is present in aliphatic chain. So if it is a terminal atom and present in aliphatic chain, so it might have a lot of fluctuations in it. So just take an example, if you want to modify this particular ligand and you don't want this fluctuation to happen, because of that fluctuation it creates instability in the protein ligand complex. So what we will do, we try to make it rigid by introducing a single bond, introducing double bond or triple bond in the molecule. Because of that, it will introduce rigidity in the molecule, and rigidity might help you to stabilize this structure. So these are the insights which you can get it from ligand RMSF value for the further modification of ligand. And one of the very critical thing here, which is PL contact. PL stands for protein ligand contact. So so for example, green color is responsible for hydrogen bonding interaction, and you can see alanine 213 residue which is having all hydrogen bonding interaction persisted throughout the MD simulation. Same way, if you see interaction with lysine 162, so there is less hydrogen bonding interaction but high hydrophobic interaction shown in purple color, and in blue color it shows a water bridge. Means water molecule is interacting with lysine molecule as well as ligand molecule. So this type of interaction analysis you can get it from this graph, and the below graph is showing you the how interactions are being changed throughout the MD simulation time scale. So on x-axis you will have time scale, let's say 5 nanosecond, and on y-axis you will have residues. And here you can specifically focus on alanine 213 residue, which has a persistent hydrogen bonding interaction, with the ligand, and we will see how it looks like in this band. So you can see this band is continuous throughout the MD simulation of 5 nanosecond, and the color, darker the color is, more the number of contact is. So you can see alanine 213 has all stable contact with the ligand, and which persisted throughout the MD simulation. But on the contrary, if you see interaction with phenyl 275, so the phenyl 275 makes few contacts, but it is not at all persistent. Means there are some white regions which are occurring in between. White region means zero contact. So it makes contact and break the contacts for some time. So I would say like this is not very persistent contact, and it is not at all that much important to stabilize your ligand. And same thing you can observe it from here. So in this graph, you can see phenylalanine 275 residue is making a hydrophobic interaction as well as water bridge interaction, but that is not even for full time. It is for just a small fraction. So these things you can analyze from this protein ligand contact graphs, and you can write it down about your interactions, how it looks like, how much time it is there, and which are the critical interactions present between protein and ligand. So other than that, in a whole summary, you will have the numerical value for all those interactions in percentage. So for example, this is the 2D interaction diagram of ligand molecule. It resembles to the 2D ligand interaction which you have seen in molecular docking analysis also on the first day. But because in molecular docking, it is about only static structure, so there are not, this percentage are not involved in it because it is just for one structure. But here, this interaction diagram for the throughout MD simulation. So for example, you can see here the ligand molecule represented in 2D, and you can see there is a interaction like hydrogen bonding interaction represented in magenta color, and you can see the number is 100%. So this number represents, it is 100% time glutamic acid 211 residue is interacting with the nitrogen of your ligand in by hydrogen bonding manner. So you can see here a legend, so which says like which interaction is represented in which color. So similarly, alanine 213 has two interactions, two hydrogen bonding interaction with two nitrogen atoms of a ligand, and this is also persisted 95% and 73%. So it means these are the very critical interactions which remains there for longer period of time. So same thing is even for water mediated interaction, which you can see here with lysine 162 and the ligand atom. So these are the things which you can analyze. You can directly show this image in your manuscript to tell reviewer that see, this is the statistics of interaction in percentage wise, and it is very well convincing that which interactions are very critical, which atoms are involved in interaction, which amino acid residues are involved in interaction. So basically you don't need to see complete MD simulation trajectory by visualization. You can get all that data in just like pictorial view. So there are other properties like torsion angle of your ligand. So you can see here you have a ligand molecule which has various torsions possible in different colors, and how this torsion angle moves around from 0 to plus 180 to minus 180 means again 0. So you can see various type of torsion angle behaviors for this molecule. So more distributed it is means more flexible it is, less distributed it is means less flexible it is. So based on this analysis, you can see where are the more flexible regions present in your ligand molecule, and those you can consider it for further modifications if necessary. So other than that, there are many other ligand properties like not only RMSD, but radius of gyration you can get, whether there are intramolecular hydrogen bonding present in it, that also you can get, molecular surface area, solvent accessible surface area, polar surface area of ligand molecule. you can get. And so these are the some minimum or necessary analysis which you need to do for any protein ligand complex to convince reviewer that your study is foolproof. But it is not limited to only these many analyses, but you can do also advanced analysis like principal component analysis, normal mode analysis, or any other type of analysis, whatever you think of. Those can also be done using advanced tools which are included in Schrodinger. So we have ready to use scripts to do those analysis, and we can discuss it further if you are interested in. But these are the few analyses which you must do for your any MD simulation. So that one need to consider. So basically it generates a complete report. Using this button, you can see there is a generate report button. Using this button, you can generate this complete report in PDF format, in images, which you can directly use it in your manuscript with a good resolution. You don't need to edit anything. You don't need to even change the resolution. It is already in images. In PDF format also you can get, in text format, in text data format also you can get all that information written just by clicking single button on generate report. So these are the various things which how it looks like in the Maestro, and I will show you some options which how easy it is, whatever I have shown in the presentation. So for that, let's say you have this is the Maestro visualizer. Let's say this is the Maestro visualizer, and Dr. has given you an introduction about Maestro visualizer, which are the various things. For example, this black color region is called as workspace, and this table type thing looking like table is called as workspace navigator, and there are various buttons like task button, job button, table button. So these are various options which are present with Maestro. So what you need to do is you just need to load your protein or protein ligand complex on it. You can see here you have a protein ligand complex in which a ligand is fitted inside the protein, and protein is shown in cartoons view. So once you have protein, as I showed you, you need to first prepare your protein. So you can prepare your protein through protein preparation wizard. So you will have that option present with you for preparation of protein, like protein preparation wizard. And in just 3 clicks, as I said, like first click on pre-process, then you have review and modify, and then you have refine. So second click is on optimize button, and third click is on minimize the structure. So just by using 3 clicks, you will have your system prepared. So you always need to remember one thing: whenever you have protein structure or protein ligand complex, you always need to prepare your protein structure preparation wizard. So once you have protein structure prepared with you, you just need to open the Desmond system builder panel that you can find it in a task option, task, browse, and on the left hand side panel you will find the option called Desmond. So in Desmond you will find various options present in it. So first option is always a system builder. So if you just simply click on system builder option, it will open the panel for you. This is the same panel which I have shown you on the presentation. And so basically if you have membrane, you can use set up your membrane from here. If you want to use water molecules, explicit water molecule, those are also present here. So there are many different type of water molecules like SPC, TIP3P, 4P. So there are various water molecules, but not only water molecules, but even other solvents, organic solvents like DMSO, methanol or octanol also you can use to solvate your structure, protein structure, if it is necessary for you to address your biological problem. Then there is a box. So there are various type of box present in it. By default it is orthorhombic, but you can have cubic or truncated octahedron or rhombic or triclinic. So there are various type of options. Normally we go with orthorhombic or cubic. So you can see here the box. Once you click on this show boundary box, it will show you how this boundary box is present in it. This is a periodic system, and that's it. You can click on minimize volume, and everything is being considered. Means your protein will be placed inside the box, center of the box. Other additional options you will have is ions. So that is also automatically calculated, means what is charge of protein and how much counter ions it requires to neutralize your system. It is also being automatically calculated and suggested that it requires minus 5, basically 5 negative ions, means chlorine ion. You can change it to any other ions like fluorine, bromine or iodine. Or if you want to add another ions, so for example sodium ions or anything else, you can also use those positive ions if it is necessary for you, if you want to change. But ideally it automatically computes and give you suggestion, which you, if you don't want to change, you don't need to change. Then it also gives you an option to add salt ion concentration. This is also very critical option. In case of experiments, we normally perform it at 150 millimolar concentration. So that also you can retain using this add salt option. So that option is also present here. So that's it. I mean, ideally all options are present there by default. If you don't want to see, you don't need to see it is there. But if you want to change any option, you are free to change any option. And at the end, you just need to choose the force field, which is OPLS3. That is the force field suggested by Schrodinger and developed by Schrodinger. So that's it. Everything is by default as such present. You just need to click on run. So once you click on run, it automatically submit the job and it will run it for few minutes. And after running this job, you will get the output, and it automatically loads that output in the Maestro. And it looks like a complete box, water box. And your protein and ligand system is present inside it. All ions are present in it, and everything is done correctly using just one click. So once you have this system ready, you just need to run MD simulation. For that, you again need to go to task, browse, and Desmond. You will have option called molecular dynamic simulation. So once you click on this molecular dynamic simulations, again, as I said, it is just 2-click thing. You just need to load your molecule from the workspace. So for example, I had just clicked on load button, and it will load the complete system in the panel, and it will show you how many atoms are there, what is the name of system. So here you can see the name of system and how many are. So it has around 47,784 atoms exactly. You just need to specify how much nanosecond you want to run. Let's say 100 nanosecond. It automatically computes how many number of frames you will get it as output. But you can always change this parameter whatever you want. So everything is being calculated automatically. You can change various ensembles to normal volume and energy, NVT, which is normal volume and temperature, normal pressure and temperature, then normal pressure, area and temperature. And this is NP gamma T is specifically for membrane simulation. So if you have loaded membrane in it, it will automatically suggest you this NP gamma T ensemble. You can have temperature, you can have pressure that you can change if you want, you can have protocol, and that's it. Means everything is basically considered by default. You just need to specify the number of nanoseconds and click on run. So once you click on run, it will run the MD simulation for you. And after running MD simulation, let's say on one GPU card, if you have, it will give you around 50 nanoseconds per day of the speed of MD simulation. And I would say this is very fast, tremendously faster than any other software. Like one can go with GPU cards for running MD simulation. So once you run MD simulation, it will give you some output trajectory, so that you just need to load it in a Maestro. So just you need to open that particular structure, and there is a T button. T stands for trajectory. It gives you the hint like double click to view this trajectory. So you just need to double click on it, and it automatically loads the associated trajectory on it. You don't need to browse it. It automatically loads everything for you. And here you can see you will get this trajectory player option. And if you play this trajectory, you will see like how it is behaving throughout the MD simulation, like what are the flexibilities included in the complete system. So now you can see like protein is also fluctuating, water box is also fluctuating, but your interest is not looking it at holistically, but you want to see it in a detailed manner, like what are the interactions happening inside it. So you can just go to preset and use apply custom preset option, and it will automatically give you the better view of ligand interacting with amino acid residue, and it will show all type of interactions present between protein and ligand. So you can see now this is the same view which you get from molecular docking analysis, but this is for the MD simulation trajectory. So you will have interacting residues and all type of interactions labeled in hydrogen bonding interactions are labeled in yellow dotted lines. So water mediated interactions are also there. Ligand is shown in stick view and residues are shown in line view. Cartoon is also present there. And then you can play your trajectory and you can see how the interactions are being changed throughout the MD simulation. So basically it plays through this player, and you can see how these frames are proceeding further one by one, and it has total 1043 number of frames. And this is the way basically you can analyze your MD simulation trajectory by visual analysis. But again, as I said, like visual analysis is great, but you need to have everything in the pictorial format. For that, we have simulation interaction diagram option that is also present in the task browse, and in Desmond you will have simulation interaction diagram. So if you simply open that panel, it asks you to load the file. So for example, you just need to load this CMS file which is generated from MD simulation output. So that's it. Simply open it, that file in this particular panel, and it takes a minute to load it, but it will show you what are the options available for the analysis. So for example, this is the same image which I have shown you on the presentation. Like it takes some time to load the complete trajectory data, but it will just give you all options. For example, this is a setup, analysis setup. Protein is picked automatically, ligand is picked automatically. You will have various type of analysis which you can do using this simulation interaction diagram, and that's it. You just need to click on run. It will do everything for you, and in background, like it will create a file which is called as this eaf.ef. You just need to open. So it also open it automatically once job get finished, but right now I am opening it through the file, and it just load everything, whatever data was calculated for this simulation interaction diagram analysis. It will open it here, and you will see how it looks like. It is the same as that I have presented in the presentation. So you can see it has various options like RMSD graph, and you can see these numbers are being changed as I move your mouse. So basically this is all interactive in nature. So same thing happens is for secondary structure element, RMSF, which is root mean square fluctuations, and you can see if I move cursor, it automatically shows me which amino acid residue is it, what is number of amino acid residue, and what is the value of RMSD value. So these are the various structures. Then you can have information for ligand contact. You can have information for secondary structure element. So in this way, there are many other type of options are also present if you want to analyze it critically. Then same thing is applicable for ligand molecule also. Here you can see which atom fluctuations, as I explained before. Then there is an option for PL contact, which is protein ligand contact. These are the various things which you can analyze at contact basis. Then you will have this 2D interaction diagram with percentage given for each interaction. That also you can use. Then various torsion angles in the ligand molecules you will have, and other ligand properties also you will have. Like surface areas and subdilatation. So these all parameters are with you. You can ready to use those parameters. And as I said, like there is a generate report button. If you simply click on this, it will give you option like whether you want to this complete report in PDF format or plots or the text data, so that you can all get it just by clicking this option and just say okay. And it will write it down everything in the PDF format. and it will automatically store it in a directory where you can simply go through that directory and analyze the complete data. Just as an example, I have already done this analysis, and you can see here, for example, various type of images which are present here, which are automatically there with high resolution images. So you can see this is the image for RMSF value, or this various torsion angles. This is for torsion angles, ligand interaction. So all type of images are automatically present in it in PNG format, or if you want all text data, if you want to use another plotting tool, that also you can get this data in that .dat format. You can simply open this file in text, and you can see all numbers are written here, which you can use it for further analysis, or you can plot that using Excel also. So you can also get this report in PDF format, and here you can see all that information which is given there is written down in the PDF format with little bit explanation about it. So what is mean by deviation, what is formula, and how to see it, and how it changes in your simulation. Like everything is automatically written down also. So you will have that PDF copy with you if you don't want to open Maestro. So it is also there. So the thing is, everything is there handy, and you can use all that information for your further analysis or publication, and it is all present there. Only you just need to do this analysis. I could say hardly 5-6 clicks, and everything will be done for you. So I hope you like that Desmond, and you'll find it easy also. So one of the very important parameter is force field, and which I would always like to highlight is we support OPLS force field, OPLS 3E, which is recently developed by Schrodinger, which has very vast type of ligands or torsions which are present in the force field, and it is very rare that these number of torsions are present in the any type of force field. So for example, there is a force field which is called molecular mechanics force field, or OPLS 2005 force field, which has very less number of torsion. So torsion means if you have a molecule, just like yesterday, told you what are the force field and how one can use force field builder to develop new force field. So these are the various torsions. So as you see, there are very less number of torsions present in it, but with OPLS 3E there are more than 100k, means 1 lakh, more than 1 lakh torsions which are present, which will almost cover all type of molecules, whether these are natural products, macrolide, or normal organic compounds, organometallic compounds, or any other. So most of the things are being covered in the OPLS 3E force field. So that is why we always suggest you to use OPLS 3E force field to get reliable and easy results. So these all things are basically possible because of that robust force field called OPLS 3E. Other than that, you can use MD simulation methodology not only to study the protein ligand interaction, but study various motions of the protein, various exploring various pockets or binding pockets, or various breathing motions, or various tunnels of the protein. You can also perform free energy perturbation simulations using Desmond MD simulation. You can also perform water map calculations. Then you can also perform induced fit and MD, IFD, MD exercise. So there are various type of things which you can perform using Desmond MD simulation, which helps you to address the particular biological problems. So other than that, these all options are present in the Desmond menu. Like you just need to go to task, browse, and Desmond. Here you will find the list of all those type of simulations, which also includes simulated annealing, then replica exchange, metadynamics or binding force metadynamics, or free energy perturbations, solubility free energy perturbations, or protein residue mutations using free energy perturbations. And there are other type of even analysis. I have shown you only simulation interaction diagram, but there are many other advanced type of analysis which you can do using Desmond. So you just need to think of doing some analysis, and I'm sure that all is being covered inside the Desmond. Basically, you don't need to look anywhere else if you are using Desmond for your MD simulation. So everything is being covered in just click button thing. And thank you all of you for listening it. And I would like to open the session for questions. If you have, I'll be happy to answer it.
Thank you so
very
much, Prajwal, for this wonderful session on Desmond and molecular dynamics. Yeah, we have quite a few questions, so we'll go one by one. And also, before going to the questions, I would like to point out in our drug discovery hackathon guidelines as well as in resources, we have listed this something called as DSHAW's molecular trajectories on COVID-19 targets. So could you give some comments on those particular trajectories which is already there available on DSHAW's website?
Yep, sure, Giri. I mean, I think it's really nice observation, and if people know about it, that will be really great. So I had a chance to go through those trajectory. It is available for free to use it, and I mean, these trajectories are there for longer time duration. Means a few hundred nanoseconds, even microseconds.
Microseconds also, yeah.
Yeah, microsecond trajectory is there for this COVID protein, and not only small proteins, but even for spike proteins, they have trajectories. So the thing is how to use those trajectories. You can simply download it, and if you are observing particular things, what is happening inside that protein during the course of simulation, you can perfectly see it in that trajectory. And I think it is also written there. You can use it for publication also, the analysis, and it is available there for free. So I suggest, definitely I suggest to go through those trajectory once if you are working on COVID proteins. So for almost for all proteins, I guess trajectories are there.
At least even 2 weeks back it got updated with few other proteins also. And also, do the user who is going to use that, do they require a graphics card for analyzing those trajectories?
So regarding Desmond, so you are talking about which trajectories?
The COVID-19 trajectories which they are going to download.
DSHAW trajectories. So correct. I mean, until and unless you have Schrodinger or Maestro with you, so that's fine. So just to see or just to install Maestro, you need at least 1 GB of graphics card, NVIDIA graphics card, which is mostly inbuilt in the laptops or computer. So that must work fine.
Okay. Great. Thank you so much, Prajwal, for that. Now I'll go to the questions. Is the ligand already present with the protein during protein preparation, or is it being added later on?
Okay. So the thing is, imagine if you have a co-crystallized ligand, means from co-crystallized ligand with protein from protein data bank, then it's all there. But if ligand is not present there, you can perform molecular docking of the ligand of your interest in protein, and then you can use that complex for protein preparation wizard, and that's the input for MD simulation.
Okay. And the interesting question, they're trying to relate it with the computational studies with wet lab studies. So in wet lab, a kind of binding affinity studies or kind of molecular docking might be possible. But whether we can do MD simulation kind of studies on wet lab, whether this is possible in reaction conditions, different reaction conditions in the lab. Is it possible or not?
Yes. So, for example, different reaction conditions can be your temperature, can be your pH, can be your ionic concentrations, and yes, these things are being handled by MD simulations.
Okay. What is the criteria of selection of force field and solvation box for MD simulation?
Okay. So, regarding force field, so until unless you are dealing with Desmond or Schrodinger, so you will have option for OPLS-3E, which I mentioned, like we always suggest to go with OPLS-3E force field because of wide coverage of almost all torsions which are available in the space, in chemical space. So we suggest to always use OPLS-3E force field. But if you are looking for something else, then in general, answer is depending on your system. So which system you want to simulate? For example, there are force field which are good for lipid. So you can go for those lipid specific force field. There are force field which are good for protein. You can go for those protein specific force fields. Similarly for ligands, similarly for polymers or etc. But until you are in Schrodinger, you don't need to worry about force field. It's all being covered in OPLS-3E force field alone.
Okay.
And
How
yeah,
can we? Yeah.
sorry, I missed the box. So
Oh, sure,
box
sure.
is
Right. Please.
yeah. So box is I mean the straight. There is no straightforward answer, but if you think like in general, so it depends on the size or shape of protein. As far as my understanding, so for example, if your protein is like looking as a circular view, so that protein, or normally globular proteins are like that, you can use cubic box. But if your protein is elongated, then generating cubic box might be computationally expensive. So you can go for orthorhombic box in such cases. But as far as my knowledge, some people also use truncated octahedron, because with this box you will get less number of water present in the box. So people might use it based on their system size.
Okay. Next is, how can we differentiate between box water and catalytic site water, which is usually important for receptor ligand interactions after MD run?
So box water means water which are present throughout the box, periodic box. But catalytic site waters are really specific one. Those are present in the catalytic site, might be interacting with ligands, and they might be considered as a bridge water, which are interacting with ligand as well as amino acid residues. So those are not really kind of water which are freely moving throughout the system inside the box. So the box water in general you can ignore those, but catalytic waters which are present inside the binding pocket are definitely things which you need to consider. Yeah. Hello.
Yeah, Prajwal, sorry. With respect to your earlier response on the hardware, there's a question came up. Can we run the software with system integrated graphics in case we don't have a dedicated graphics card?
You need like dedicated graphics card, but I think to get a specific answer, if you write me an email, I'll connect
Sure.
you to a technical expert and he can comment on it.
Another final question. What is the ideal temperature to equilibrate the viral protein? Is it the same as human protein or something different?
Okay, so the answer lies in experiments. So on which temperature experiments are being considered? So you need to go to literature or assay methods and see it, like what temperature they are using it. So that's the information which you needed before going for MD simulations. So that's the answer.
Okay. Okay, great. So thank you so much, Prajwal. So thank you for the session, and we will be moving on to the next session by Dr. Pritesh, and that will be a separate YouTube link